In this video, we look at some more problems from section 4.5 called on L'Hopital's rule. Okay, so we're familiar with at this point from previous videos that if we have the limit as x goes to c of some function f of x divided by g of x, and that function f divided by g is of the form 0 over 0 or infinity over infinity, that we know that we can use L'Hopital's rule to compute the limit as the derivative of the function divided by the derivative of the other function. And then hopefully this new limit will exist. If this limit doesn't exist and you get another indeterminate form, you can keep trying L'Hopital's rule, right, until you get a limit that is doable. Okay? So let's take a look at an example now of number 12. Okay, they're basically in the direction saying determine whether or not each expression is indeterminate. Okay, and if it is indeterminate, determine which type of indeterminate form it is. Okay, so we're seeing here that essentially we are being asked to compute the limit as x gets closer to c is equal to 0 in this case, of the logarithm divided by e to the x minus 1. And we are seeing that as x gets closer to 0, that the logarithm of x plus 1 is getting closer to the logarithm of 1, which is equal to 0. And we're also seeing that as x gets closer to 0, e to the x minus 1 is getting close to e to the 0 minus 1, which is also equal to 0. So we are seeing that this limit is of the form 0 over 0. All right, so what we'd like to do now is to try to compute this limit using L'Hopital's rule. Okay, let me figure out how to add a page below. Alright, so diving in, adding a new page, let's try to evaluate this limit. Okay, we have the limit as x gets closer to 0 of the logarithm function, logarithm of x plus 1 divided by e to the x minus 1. Okay, and we do recognize that this is a 0 over 0 indeterminate form, so we need to try to do L'Hopital's rule and compute the derivative of the top function, which is 1 over x plus 1, multiplied by the derivative of x plus 1, which is just 1, and then divided by the derivative of the bottom function, which is just e to the x. So this leads us to a new limit to try to compute. Limit as x goes to 0, 1 over x plus 1, multiplied by the reciprocal. Okay. So this leads us with a little bit of algebra to a new limit to compute e to the x, 1 over e to the x times x plus 1. Right? And now we need to reevaluate the situation and then say, is this limit computable? Can we compute this one? And as x gets closer to 0, we're seeing that 1 gets closer to, the limit as x goes to 0 of 1 gets closer to 1, and e to the x gets closer to e to the 0, which is equal to 1, and then x plus 1 gets closer to 1, so here we have our limit equal to 1. So we can conclude that the limit as x goes to 0 of the logarithm of x plus 1 divided by e to the x minus 1, according to L'Hopital's rule, is just equal to 1. Okay, so there's another pretty straightforward example. And there are a whole variety of different problems that we can try to compute. Okay, we can look at something like number 48. Okay, so we're going to try to compute the limit as x goes to 0 of the cotangent of x minus 1 over x. Okay. Now, cotangent, doing just a little bit of pre-work on this problem, limit as x goes to 0. Cotangent is the same thing as the cosine of x divided by the sine of x minus 1 over x. And we're seeing here that as x gets closer to 0, 1 over 0 is getting close to infinity. Okay. And cosine of x as x gets closer to 0 is getting close to the cosine of 0, which is 1. Sine of 0 we know is 0. So again, we're seeing that we're getting 1 over 0, which is an infinity. So we are seeing that we have a new indeterminate form, infinity minus infinity. This is indeterminate because we're not sure exactly what this is going to be. Depending on the nature of the infinities, this may go to 0, this may go to some number, it may not exist. Completely depends on the nature of the infinities in this problem. Okay, so what I would like to do is try to go to another page and let's try to evaluate this limit. Okay, so we have the limit of an infinity minus infinity form. We have the cosine of x divided by sine of x minus 1 over x. And the only way I know to begin thinking about this indeterminate form is to maybe just try some algebra. Just put this into another form that maybe we have a chance of working with. Okay, it's the only thing I can think to do here, and the algebra I'm seeing is to essentially get a common denominator. Okay, so the algebra common denominator. Okay, so let's see, we'll get x cosine of x minus sine of x. Okay. Here is our algebra problem. Okay. And the advantage here is that we have basically turned infinity minus infinity, and we have turned that into a fraction problem. Okay, getting the common denominator. And that fraction we can see as x gets closer to 0, we get 0 times 0, which is 0. So this x times sine of x gets closer to 0, and the numerator here, 0 minus 0 is 0. We have a new indeterminate form that we are now familiar with. Okay, so we can now do L'Hopital's rule. Okay, and we need to take the derivative of the top function, okay, which is going to require a product rule here. Derivative of cosine is negative sine, so there's first times the derivative of the second, plus the second times the derivative of x, which is 1, minus the derivative of sine is cosine, and there's some hope there. We can see maybe some potential algebra happening to cancel out. Product rule again on the bottom is first derivative of the second plus the second times the derivative of the first. And we can see that there is some algebra that happened. The cosines canceled. And the question is, we now have a new limit. And is this limit going to be possible? X times sine of x divided by x cosine of x plus sine of x. Okay. And again, we need to look at what happens as x gets closer to 0. Let's see where this is going to lead us. We get 0 in the top because of the x. I'm seeing an x. I'm seeing a 0 in the bottom from this term. I'm seeing a 0 in the bottom from here. So I'm seeing another 0 over 0. Okay, which is another chance for us to try L'Hopital's rule and see what's going to happen. Okay, so we'll get The limit as x goes to 0. First times the derivative of the second plus the second times the derivative of the first divided by, okay, let's see what happens here. First derivative of cosine is negative sine. First times the derivative of the second plus the second times the derivative of the first, and then the derivative of sine is cosine. And now we need to look and see what happens when we just try to put this into another form. Just do a little bit of simplifying of these minus signs. So this will be minus sine of x divided by negative x sine of x plus 2 cosine of x. And now we're going to see what happens finally as x gets closer to 0. We're seeing again, we're getting a 0 from here. Sine of 0 is equal to 0. So this is not looking promising, right? 0. But the denominator, here's another 0, so I'm a little nervous. But right here, finally, 2 times cosine of 0 is equal to 2. And 0 over 2 is no longer an indeterminate form. 0 divided by 2, 0 divided into 2 parts is just 0. So we can conclude that the limit as x goes to 0 of the cotangent of x minus 1 over x is actually equal to 0. Okay, so we're seeing that this function of x that this function right here, that this function is not defined at 0. F of 0 does not exist. But the limit does exist, and that limit is equal to 0. So in this video, in the next video, we'll look at an actual application.